So section 5.1, evaluate each integral. Now in each of these we're going to use the so-called power rule for integrals, or power rule for computing antiderivatives. See if I'm careful with the details here. If we want the integral of x to the power of m dx, I need for m not to be equal to -1. That's going to cause a problem for us because we're going to need to divide by m plus 1. If m equals -1, then m plus 1 equals 0, and we cannot divide by 0. So I need to exclude the case that m equals -1. It will be dealt with separately. But if m is not equal to -1, what we would do, talked about this last time, if we're taking the derivative, we would first multiply by m and then subtract 1 from the exponent. We've got to reverse those operations in reverse order. The opposite of subtracting 1 from the exponent is adding 1 to the exponent. The opposite of multiplying by the exponent is dividing by the exponent. And of course, we need a constant of integration. If we find an expression whose derivative is equal to the original, then adding any constant is also going to have a derivative equal to the original. So we must have the constant of integration. Basically, this represents the set of all expressions whose derivatives are equal to the integrand x to the m. So the first one is laid out exactly what we need. We would add 1 to the exponent and then divide by that new exponent that we got, and then add the constant of integration. So it's going to be 1/6 times x to the 6th plus c. And usually it's going to be easier to check our answer than it is to find our answer. If we can quickly calculate the derivative, we would take 6 and multiply by 1/6, then get 6/6 or 1, and then subtract 1 from the 6 to get 5. So it's pretty easy to check that the derivative of this, regardless of what c is x to the 5th.
Thank you.
Go. The second one. Well, we don't have an expression where we have x to the power of m in the numerator. If it's a fraction, it needs to be in the numerator. If it's not a fraction, well, let me just say this. If it's a fraction, it needs to be in the numerator. If it's not a fraction, it's not an issue. It is a fraction, but we don't have x to the 3rd power in the numerator. What we need is this, the integral of x to the -3. There. If we have this, then we can apply the power rule. So add 1 to the exponent, and we get x to the -2, and then divide by that new exponent that we just got, and then add c, and then simplify. The 1 over -2 is equal to -1/2. But when we have the x to the -2, that's going to shove that down in the denominator. I can include an extra step. You probably don't need to write this extra step. -1/2 times 1 over x squared plus c, and then multiply those fractions together to get -1 over 2x squared plus c. To check that, we kind of have to undo some of what we've done. Probably you'd want to look at just the first step there and see if you can take the derivative of that, multiply the -2 by the -1/2 to get 1, subtract 1 from the exponent to get -3, and then shove it down the denominator and call it 1 over x cubed. The last one, x to the 2/3, add one of the exponent, x to the whatever 2/3 plus 1 is, and then divide by whatever 2/3 plus 1 is. Tack on the constant of integration plus c. So this is going to be, well, let's figure out what 2/3 plus 1 is. 2/3 plus 3/3 is how many thirds? 5/3. So we're actually dividing by 5/3, and that's equivalent to multiplying by 3/5. So this is 3/5 x to the 5/3. Hang on to that constant of integration all the way down. Looks like this. If we were to multiply the 5/3 by the 3/5, we'd get 1. And then if we subtract 1 from the exponent, we'd get 2/3. So 1x to the 2/3 would be the derivative of this, and that's what we want to happen. Are these hard problems or easy problems? Easy problems, good. Properties of the indefinite integral. It's a linear operation. Integration, just like differentiation, is a linear operation. Basically, if we apply it to the sum of two expressions, then it's equivalent to applying it to the individual expressions and then adding those two results. Likewise, the integral of a constant times a function is equal to the constant times the integral of that function. So just kind of a quick note, the integral of a sum is equal to the sum of the integrals, and the integral of the difference is equal to the difference of the integrals. In the next couple of cases, I'm really going to emphasize these properties to kind of an extreme extent that we wouldn't do in regular practice, but just want to emphasize that we are relying on these properties in order to say what we'll say about integration, but eventually we'll just take these properties for granted and we won't show all the details because it can be a real pain. So the first one, we use property A, the integral of a constant times a function is equal to that constant times the integral of the function. So step 1, we can take the 3 that's inside the integrand and pass it through the integral. Just like we could do if we're taking a derivative. We could pass the 3 in front of the ddx. So this equals 3 times the integral of sine x dx. So we don't have to stop and think, I wonder what we could take the derivative of to get 3 sine x. We just have to stop and think and ask ourselves, I wonder what we could take the derivative of to get sine x. So what can we take the derivative of to get sine x? Negative cosine x. If we take the derivative of negative cosine x, ddx of negative cosine x equals sine x. Yes, it does. It's the negative of the negative sine x. So it's sine x. So it's going to be 3 times. So I'll put a big set of brackets or parentheses. Maybe parentheses. Negative cosine x plus c sub 1. So I put a constant of integration there, and there are going to be a couple different constants of integration in this problem, so I'll denote the first one that I run across as c sub 1. Of course, we would want to distribute the 3 across the parentheses. There's no need to leave this in parentheses like this. So I'm going to say this is negative 3 cosine x plus 3 c sub 1. But the thing is, 3c sub 1 represents an arbitrary constant. And it's kind of silly just to say 3c sub 1 could be anything. It would be better just to rename it, call it c. Let, off in the margin, let c equal 3c sub 1, and just say negative 3 cosine x plus c. So, take the derivative of negative 3 cosine x plus any constant, and you get 3 sine x. That's what we're saying. in practice, we don't have to, if we know what we're doing, we don't have to think so hard about the 3c sub 1. Now, there's some situations where it's kind of important to know exactly where the constant integration should go at each stage in the process. So if there's any doubt, probably do want to go through and really emphasize that, that this is where it is, but we're going to go with it just like that. Next, we're going to do a combination of things. Well, maybe just the last one. The integral of the difference equals the difference of the integrals. I'm going to take for granted the constant times the integral and just apply the power rule as though it's okay to use a constant in front of it. I'll save us a little bit of time. The integral of the difference is equal to the difference of the integrals. The integral of 3x to the 5th dx minus the integral of 2x to the 4th dx. Separate the two integrands. Because I can't apply the power rule to either one of them individually because, we can't apply the power rule to that difference because that's not x raised to a power. But we can apply the power rule to them separately. I'm wondering to myself, do I want to take the 3 out in front? Do I want to take the 2 out in front? Or do I just want to say 3x to the 6th and divide by 6? I think I'm just going to say 3x to the 6th and divide by 6. So here goes. 3x to the 6th over 6 plus c sub 1 minus 2x to the 5th over 5 plus c sub 2. If you watch the video on this one, I may have done it differently in a previous semester. I may have gone ahead and taken the 3 out in front, taken the 2 out in front, and I would have found myself dealing with a 3c sub 1 and a 2c sub 2, kind of like in the previous example. But it won't be long before we've done enough of these where we realize it's not something we technically have to do. This is 1/2 x to the 6th plus c sub 1 minus 2/5 x to the 5th minus c sub 2. So let c equals c sub 1 minus c sub 2. And what do we have? 1/2 x to the 6th minus 2/5 x to the 5th plus c. So when we boil this down, we just need any old expression that we can take the derivative of and get 3x to the 5th minus 2x to the 4th. Anything will work. If we take the derivative of 1/2 x to the 6th, we get 3x to the 5th. If we take the derivative of negative 2/5 x to the 5th, we get negative 2x to the 4th. So if we take the derivative of 1/2 x to the 6th minus 2/5 x to the 5th, we get the integrand that we want. Tack on any constant of integration, and we're good. The process, it just says we can use these rules. The integral of the sum is equal to the sum of the integrals. The integral of the difference is equal to the difference of the integrals. And so we can integrate term by term, just like we can differentiate term by term. And it greatly expands the scope, the kinds of functions we can integrate. Might have to use a little bit of trickery here to get at these. The integral of, the A part, there's something I've not told you, but I think we have enough information to get this done, and probably I did this deliberately. It's going to be the integral of 3t over t squared plus 7t cubed over t squared dt. Basically, taking that fraction, noticing that we have a monomial in the denominator. If it's a binomial in the denominator, it's just going to be ugly, and there might not be a real nice way to get around this. But just a monomial in the denominator, involving that variable, we can break it apart and write it as the sum of two fractions and reduce those individual fractions and come up with separate expressions that we can integrate term by term. First one is going to be the integral of 3 over t The other one is going to be the integral of 7t. So the integral of 3 over t dt plus the integral of 7t dt. Well, here's the thing. 3 over t, that's like 3t to the negative 1. And we said that if we're applying this power rule, where did I say it? Right there. The exponent's not allowed to be negative 1. That's a problem. That's a problem. The exponent is negative 1. So what we'd have to think about is what we could take the derivative of to get t to the negative 1, or what we could take the derivative of to get 1 over t. And it's not a polynomial. It's not a rational expression. What very important function have we taken the derivative of at some point in this course and gotten 1 over t as the answer?
Natural log.
Is it the natural log? Derivative of natural log? Yes, 1 over that expression. So, let's stare this down and see if this would not be 3 times the natural log. Now I could say the natural log of t, just plain old t there, but actually I think we went beyond that and said not only was it true that d dx of the natural log of x is equal to 1 over x, but we doubled the domain. Remember when we doubled the domain? We said not only that, but actually the derivative of the natural log of the absolute value of x is equal to 1 over x. It works on an interval where x is positive. It also works on an interval where x is negative. For this antiderivative, we'd like to do it for as much of the domain of 3 over t as we can. We'd like it to apply when t is positive. We'd like it to apply when t is negative. So we put absolute value bars. Because whether t is, it's an interval where t is positive or it's an interval where t is negative, if we take the derivative of 3 times the natural log of the absolute value of t, we'll get 3 over t. We don't need absolute value in the integrand, but we can put absolute value in this antiderivative, and it'll double the domain without costing us anything. Plus, now here, the exponent is not negative 1, it's positive 1. So we add 1 to the exponent and divide by the new exponent that we get. 7t squared over 2. And notice I've already begun to be cavalier with my use of the constant of integration. Technically, I should probably put a plus c sub 1 after this first one, and a plus c sub 2 after the second one, and let c equal c sub 1 plus c sub 2. But I'm just going to say plus c.
Why isn't 7t cubed?
Well, because we've got a 1 there. Oh, which one is not 7t cubed?
The one on the bottom.
The one on the bottom?
Well, both of those, I guess.
Because I'm just adding 1 to the 1. Just adding 1 to the 1. So it'll be squared.
And then A on the top left.
A on the top left, this one?
Yeah.
Well, it's just this 3 minus this 2.
Yeah.
Gave us a t to the first power to work with.
Oh, okay. Forgot we were simplifying those.
So this will work. The B part simply involves trickery. There's no really good suggestion. There's probably other ways of approaching this, maybe some way more complicated ways. But the 1 plus cosine x, it's really kind of tough dealing with these when there's a binomial expression, multiple term expression in the denominator. If there's some trickery that'll work, then I would suggest doing it. So, anybody know what I'm about to do here?
A trig identity?
Well, kind of, yeah. Basically, we want to use the Pythagorean identity, and we can get at that Pythagorean identity with something like this. We could write this in terms of the 1 minus cosine squared x. That would give us the single expression sine squared x in the denominator. And so once we get that, then maybe we could rewrite this like we did the previous one. If we have 2 terms in the numerator and just 1 in the denominator, we can write it as the sum or maybe difference of a couple of fractions and then deal with those individual fractions. But with multiple terms in the denominator, it's beyond the scope of Calc 1. There'll be different techniques in Calc 2 for dealing with that sort of situation, but it's really beyond the scope of what we do here. Integral of 1 minus cosine x over, okay, we know it's going to be 1 minus cosine squared x. And we know that's going to be sine squared x. So I'm going to skip that step and just say sine squared x right there, dx. Let's see if there's hope for taking this and writing it as the difference of two separate fractions. The integral of 1 over sine squared x minus cosine x over sine squared x dx. Okay, if you just ask me, I'm not going to have any idea what we can take the derivative of to get 1 over sine squared x, but I might be able to think of it and figure out what we might be able to take the derivative of to come up with cosecant squared x. That looks more like something on our list of derivatives of the half dozen trig functions. And for this other one, let's see, cosine x over sine squared x, if that could be written as, what do I want there? Does cosine x over sine x times 1 over sine x help?
Cotangent is negative cosecant squared.
I think this could work. Cotangent, oh, so for the first one, got the wheels turning on that one, that could be cotangent x or maybe negative cotangent x. Someone would have to work out the sign somehow, SIGN. For this second one, I'm going to say this is weird, but humor me here. Negative 1 times negative cosecant squared x minus or plus negative cotangent x cosecant x dx. Have I successfully spoiled the problem for you now? I just want the next step to be as clean and neat as possible. I suppose in real life, even math is never this clean and neat. We should just rough it out here. What can you take the derivative of and get negative cosecant squared x? What was it, Patrick?
Oh, negative cosecant. Oh, cotangent. Oh, negative cotangent.
So it's going to be negative cotangent x.
Oh, to get the negative cosecant?
Yes. So just plain old cotangent x. Plain old cotangent x. What can you take the derivative of to get negative? I think the way we said it was it negative cosecant x cotangent x?
Yeah.
We memorized it? I think that is the derivative of cosecant x. So maybe the cleanest, neatest way to write this would be cosecant x minus cotangent x plus c. It would take a little bit of work to take the derivative of this and try to make it look like 1 over 1 plus cosine x. More work than we have time for right now. It's a good time for a break. I think there might be a good GeoGebra example here. Let me take a moment and think about it. All right, when you look at your list of things to do, courses to take in your mathematical future, who has differential equations on your list of things to do? Whoa, bunch of folks, okay.
No.
And those who's happy that differential equations is not on your list of things to do. All right. All right, good. Basically, what we're looking for here, we're trying to solve this differential equation. The derivative is given f prime of x, and we're looking for the function that will satisfy this equation in which a derivative is involved. So it's not one of the more challenging differential equations that one might run into, but strictly speaking, it is a differential equation. A general solution would be the set of such functions that may satisfy this. A particular solution would be, any one solution, but we want the particular solution that satisfies this initial condition, kind of a starting point where we have a specified value for the function that we're looking for at a particular number in its domain. So if f prime of x equals 3x squared minus 4, we could do it something like this. The integral of f prime of x dx equals the integral of 3x squared minus 4 dx. Basically integrate both sides with respect to x. When we do this, a function, an antiderivative would be a function whose derivative is f prime. So big F of x is going to be, and I don't need constants of integration on both sides, either side would be fine, is going to be 3x cubed over 3, add 1 to the exponent, divide by the new exponent that we found, minus, 4x, I just ruined the problem for myself, minus 4x plus c. I think I can fix it though in the GeoGebra example. So one more thing, big F of x equals x cubed minus 4x plus c. So any one of these, for any value of c, it's going to satisfy f prime of x equals 3x squared minus 4. Infinite supply of these. We need the one, basically we're looking for the value of c that will give our function a value of 3 at 1. So, not too tough to find, f of 1 equals 1 cubed minus 4 times 1 plus c, and we'd like that to equal 3. What value of c is going to make this happen? It's looking like what? Maybe c equals 6. So if that's the case, f of x equals x cubed minus 4x plus 6. X cubed minus 4x plus 6 is a particular solution. It's the particular solution that satisfies this initial condition. So basically there's a knowledge of what the derivative of the function is, and there's also the knowledge of what the value of the function is at one particular number in its domain. So this is the answer that we want. Now, what I was trying to do during the break is come up with a GeoGebra worksheet that had a lot of different functions that would satisfy that the derivative is 3x squared minus 4. I left off the minus 4x though. I think it's an easy fix. Let me see. It may not be. I might just have to redo this. Let's see. I don't think I can just go in here and edit.
Object properties.
Maybe. I might be able to. What if I put in a, was it minus 4x plus c? There we go. And then for this one, put in a minus 4x. I've got the plus a there. All right, so what I would want is the one, and let's go ahead and display it. Let's say big F of x equals, what did it call it? Little f, I guess. Little f, and make it large. Make it large. All right. So for the one, and I maybe should make it the same color as the other one. So the red one is f of x equals x cubed minus 4x plus 1. And if I move this, adding or subtracting a number to the right-hand side is going to be a vertical shift, up or down, depending on what we add or subtract. A lot of functions that have the indicated function as their derivative, but the one we want is apparently not going to show up unless I increase this maybe to at least 6, how about 7? There we go. So if we go up there, the one we want is f of x equals x cubed minus 4x plus 6. So all this family of functions that have that particular quadratic as their derivative are all going to be vertical translations of each other. It's not news, I'm sure you were thinking that. It's kind of interesting, I think, to visualize it, though. And let's see if we can do this projectile motion problem where I actually use meters instead of feet. Okay, here goes. Rock is thrown upward from an initial height of 40 meters with an initial velocity of 20 meters per second using negative 9.8 meters per second squared as the acceleration due to gravity near the surface of the Earth. Find an expression for the height, S of t, of the rock in meters as a function of the time in seconds. So we have A of t equals negative 9.8. I'm going to suppress the units for simplicity. We'll include the units in the final answer. Sometimes I want to include the units because there's some particular significance, and there is kind of. If I miss them, I'll put them back in. But for now, I'm going to suppress them. A of t equals negative 9.8. So v of t equals, well, we take the derivative of the velocity to get the acceleration. The acceleration is the rate at which the velocity is changing with respect to time. We differentiate the velocity to get the acceleration. It would make sense then that we should integrate the acceleration to get the velocity. So v of t equals the integral of a of t dt. So v of t equals the integral of negative 9.8 dt. So v of t equals, have we integrated a constant? Have we done that? What kind of function can you take the derivative of and get a constant?
E of.
It would have to have like
E to the power of something.
Oh, well, you take the, I see what you're thinking. We take the derivative of e to a power, and what you get is a constant times that expression. I'm just thinking just a plain old constant. What types of functions have constant slope? A line. A line. So a linear function is what we need. So how about negative 9.8 t plus c? Negative 9.8 t plus c. But we can be more specific because we have an initial condition. The initial condition on the velocity, initial velocity of 20 meters per second. What we know is that v of 0, v naught, if you will, is equal to well, let's do this. For the sake of space, negative 9.8 times 0 plus c, and it's given to be 20 meters per second. That's enough information to solve for c. Basically, 0 plus c equals 20, so c equals 20 meters per second. So finish up the velocity function by saying that with the given initial condition, v of t is negative 9.8 t plus 20, where the velocity will express the, v of t expresses the velocity in meters per second. Now, if we have the position function, we can take the derivative of that to get the velocity. The velocity is the rate at which the position is changing with respect to time. So the derivative of the velocity is equal to the derivative of the position is equal to the velocity function. It should hopefully make sense that if we integrate the velocity function, we could get the position function. So S of t equals the integral of v of t dt. So S of t equals the integral of negative 9.8t plus 20 dt. We need a function that we can take the derivative of to get negative 9.8t plus 20. Power rule, negative 9.8t squared, add 1 to that exponent and divide by that new exponent that we got. What can you take the derivative of and get 20? So we'll go to about 20t there, plus a constant, different constant, but a constant, S of 0 equals negative 4.9 times 0 squared plus 20 times 0 plus c, and we're given that what? The initial height, the initial position would be a positive 40 meters. So 0 plus c equals 40 meters. So c equals 40 meters. So S of t equals negative 4.9 t squared plus 20t plus 40. Where if we input the time in seconds, this will give us the position relative to the origin in meters. So basically, if we want to do this in more generality, what we would have is negative 1/2 g. If g is the constant acceleration, 20 would be the v sub 0, the initial velocity, and 40 would be the s sub 0, the initial position. S of t equals negative 1/2, and maybe I should just say a t squared plus v sub 0 t plus s sub 0, a function you'll probably come to know and love in physics. Let's see what needs to be said about sigma notation here before moving on. We're going to work our way toward coming up with an expression for the area under a curve, the area bounded by a continuous, the graph of a continuous function and the x-axis. And we'd like to be able to use integration, ultimately, to be able to do the calculation. In some specific cases, it can be done without having to do integration by using sigma notation and calculating the limit. But let's see if we remember this from pre-calculus. The expression sigma of k cubed from k equals 2 to 6 has various features, and if I can copy and paste this, I can point to them as I describe them. There is the lower limit of summation, which is 2. The upper limit of summation, which is 6. There is the index of summation. I don't know why that was not put in boldface type. The index of summation is k. Typical letters used for the index of summation: I, J, K, M, and N. There might be others that could work, but those, I believe, are by far the most common: I, J, K, M, and N. And, of course, capital Greek letter sigma, denoting that it's the sum. Basically, we take the expression over which we're calculating the sum, and beginning with the lower limit, we substitute that number for the variable Substitute 2 for k, we evaluate the expression, we get 2 cubed. We substitute 3 for k, we get 3 cubed. Now the increment is 1 each time. Plain vanilla sigma notation. We increment by 1 each time. Increase it to 4, increase it to 5, increase it to 6, and then stop, because 6 is the upper limit of summation. And then the value of the sum is what we get when we crunch all those numbers. Hopefully I did that correctly to get 440 would be the value of that sum. Sigma notation will give us a convenient way of expressing the sum of various either rectangles or trapezoids that we may inscribe in the regions over intervals underneath the curve to be able to calculate or approximate the area bounded by the graph of a continuous function and the x-axis. Practice with these sums. We really do this in pre-calculus a good bit. I don't know if I want to trouble you with these particular calculations. There are other things, trust me, that I will trouble you with, so I don't know if I want to trouble you with those. Properties of sigma notation. Sigma of a constant times an expression is the constant times sigma of the expression. Sigma of a sum equals the sum of the sigmas. But these, I think, are familiar enough where we don't need real specific examples of these. I may not even have to use these summation formulas. We do these in pre-calculus to some extent. There is an example I can think of where we might use one of these, but we may not, so I would keep moving.
Of course, weren't there ways also to plug that into the calculator?
Yes. Yeah, they're nice ways to do this using the calculator. Evaluating the limit sometimes in terms if there's an unknown here, we might not be able to do that with the T83s and 4s, 84s. Keep moving. Express each sum in closed form. All right. I'm going to paste this and then shrink it down to small print. Thought I was. I want to be able to refer to it. As I draw the picture. What we want to be able to do is this. We want to be able to write an expression for an approximation of the area bounded by the graph of a continuous function and the x-axis over a closed interval, let's say from A to B. So here's A, and here's B. And we're going to say A is equal to x sub 0, and B is equal to x sub n. And we're going to begin by partitioning the interval into intervals of equal size, subintervals of equal size. Ultimately, we'll relax that, where all we need is just a collection of points along the x-axis between A and B, and they don't have to be spaced equally apart. But for now, if I can do this, and it doesn't have to be, well, let's see. Let's see if I can do this so that they look like it's reasonably well done. All right, so this would be x sub 1, and x sub 2, and x sub 3, x sub 4, and eventually we get to x sub n. I guess this would be x sub n minus 1. So what does the curve look like? Well, it could look something like that. And I might as well start at A, huh? Start at A and go over there to B. Could look something like this. And if we wanted the total area bounded by that curve and the x-axis, we don't have a convenient formula from geometry. to come up with that calculation. It really depends a lot on the nature of that function. So we divide up into intervals like I've done, and then we approximate the area above each of those intervals using a rectangle. There are other ways to do it. We could use trapezoids, which does a little bit better job, but we use rectangles. So let's see. I would like to choose a point in each of the intervals. So I'm going to pick a point right here. I think for simplicity, it might look good if I choose the midpoints. I don't have to choose the midpoints, but I'm going to do that. I'm going to choose the midpoint here, and I'm going to evaluate the function at that midpoint, and then draw the rectangle that's directly above this interval, like this. And I'm going to choose this midpoint and evaluate the function there, and then draw the rectangle that's directly above that interval. And choose this midpoint, and that gives a rectangle. And let's see, this midpoint, right across like that, that gives a rectangle. And this midpoint, that gives a rectangle. And finally that midpoint, and that gives a rectangle. If we add up the areas of those 1, 2, 3, 4, 5, 6 rectangles, it's likely not going to be exactly the area bounded by the curve and the x-axis, but it should be close. It looks like it should be close because this rectangle, it's going to overestimate it by this much. It's going to underestimate it by that much, and if those aren't far apart, they'll offset each other. And so it should be reasonably close. And there are other ways to do this where they'll miss it by more than that, but I think these midpoints are pretty good. If you look right here, these midpoints that I've chosen, they don't have to be exactly the midpoints. They could be anywhere in those little subintervals. But this first one is called x sub 1 star. And the next one is called x sub 2 star. And so on until the last one is called x sub n star. It's important to know exactly what those values are because we would evaluate the function at those values, and that tells us how high, the function values tells us how high the rectangles are. So the area of any one of those rectangles would be, well, let's say, let's say it's like this. I guess I'll just need to point to it. If I evaluate the function x sub 1 star, it gives the height of this rectangle because that's the height, that's the value of the function there. If I multiply by the length of the interval, I'm going to call that delta x, and that's going to be b minus a divided by n. If they're all the same, then it's the length of the entire interval, that's b minus a, divided by however many there are. If there's 6 of them, it's b minus a divided by 6. So delta x is b minus a divided by n. It's the length of each one of those little subintervals. The height of that rectangle times the width or the length of the little subinterval is going to be the area. If we add that to f of x sub 2 star times delta x and keep doing that until we get to f of x sub n star times delta x, then we could represent the sum of the areas of those n rectangles using sigma notation. Sigma k equals 1 to n of f of x sub k star times delta x. Now if they have constant width, the delta x even could be passed in front of the sigma notation. If that doesn't change as the value of k changes, then we could even bring that in front, but it's ultimately not going to be necessary. We're going to want to allow for the possibility that delta x could depend on k, although it does not in this case. So we do this for one collection of, for one value of n, for n equals 6. And then we think, well, that was a pretty good approximation. How could we come up with a better approximation? If we did it for n equals 6, what might give us a better approximation than n equals 6? Is it possible that n equals 7 or 8 or 9 or 10 might give us a better approximation than n equals 6? If we make the rectangles skinnier, is it possible that if we look at how much we miss it there and how much we miss it there, there'll be less of a disparity between those if the rectangles are skinnier? It turns out to be the case. It turns out that if we evaluate the limit of this expression, if it exists, as n approaches infinity, if it's a continuous function, then this will actually be what we can define to be the area underneath the curve. Let's look at the theorem here, or actually not theorem, definition. We're going to define the area under the curve as the limit of this expression that we just wrote down there as n approaches positive infinity. Basically, take the limit as n approaches infinity, and that's going to be the area. So we would do this in such a way, choose n large enough to give us the amount of precision that we're looking for. Now, we're going to be looking at a way of doing this. We actually have to express this x sub k star in such a way that if we're using a calculating utility to do this, we can actually tell it what's the value of x sub k star if k equals 1? What's the value of x sub k star if k equals 2? What's the value of x sub k star if k equals 3? And we could express x sub k star in terms of, well, what information do we need? The left endpoint of the interval, the right hand endpoint of the interval, the value of n, how many subintervals are there, and is it going to be the midpoint of each little subinterval? Is it going to be the left-hand endpoint? Is it going to be the right-hand endpoint? Let's consider the situation where it would be, I'm looking at our time. Let me just do this. I'm gonna have to come up with expressions next time. We want to be as thoughtful as we can about this, but it's been a while, probably this time last semester, since I've looked at this. But it'll give me an opportunity to look at it so I can think how I might improve on it. I wonder what's the best one. Area under a curve, that's probably the best one. Hope this works. We need to tell it how many intervals. Let me do something that's that doesn't dip below the x-axis for now. We're just considering one that's above the x-axis. So let's say, what if that's plus 3 would probably do it, huh? Maybe not. Plus 12? Oh, that's better. Okay. So the function's positive on a closed interval. I need to tell it the endpoints of the interval. So 4 to 10. And then I need to decide, do I want to use the midpoints? Or do I want to use maybe the left endpoints? Or the right endpoints of the interval? And how many little subintervals do I want? Well, GeoGebra actually gives us a pretty good way of telling how this is going to work. A little bit later in the chapter, we'll use an antiderivative to find the exact area. And if we'll believe GeoGebra, the exact total area bounded by the curve of the x-axis is 132 square units. And it looks like it's pretty close for the midpoint approximation. What if we used The left endpoint approximation, if you look and see as we drag it over, if we use the left endpoints to calculate the heights of those rectangles, it's significantly going to underestimate the total area bounded by the curve in the x-axis, because there's nothing to compensate for the fact that each rectangle is completely underneath the curve, 109 versus 32. On the other hand, if we use the right endpoint approximation, it's way going to overestimate, because you look at those rectangles, everything above the curve is too much. But the midpoint approximation, I think, does about as good a job as anything. Now, what happens if we increase the number of rectangles? 6 rectangles here, 3 rectangles, 1 rectangle. Just use 1 rectangle, it's not that great. But if I go the other way and use maybe 21 rectangles, that's pretty close to 132. If we go with what? 41 rectangles, it's even closer to 132. And if we just push the envelope to 100 rectangles, 200 rectangles, I don't know where I put the limit was, 250 rectangles, then when it does the calculation, very little difference between the sum of the areas of all those little rectangles and what calculus would tell us is the exact area. Well, this is doing it the easy way. We'd like to be able to come up with expressions so we can program our calculators to do this, but this is kind of the idea of what we're doing.